Hello, Professor Rees. Are you there?
Yes. Can you hear me?
Okay, sir. Thank you. So we'll start by 2:30.
Yep.
We'll wait 6 minutes more.
I've not used Meet before, certainly not to present. I presume the Present Now button is the thing to press.
Yes. So just
Greeting.
we'll wait 5 minutes more, then we'll start, sir.
Yep, sounds good.
Yes. Thank you.
Hopefully I can work this system correctly.
Yes.
Let's see what the volume is. My volume's low. Maybe that's better. Maybe I need to just check that I can get everything on the screen. So I'll press the Present Now button and see what happens.
Yes.
Um,
There is a tab in right bottom corner.
yeah.
Present now.
Yep.
So you click present now. Then there are three options. Your entire screen, and second option is window. So when you click
Right.
the window, then you can see your PPT.
Right. My entire screen. Right. Let's just try that. Select window or screen. Entire screen. Okay. Right. What can you see now?
Sir, actually, have you opened your PPT in your system?
It's a PDF. Yes, I have.
Okay. Then you go to present now. There is a tab in right. Yes. You
Right.
click it. Then there are three options. First option is your entire screen.
Yep. I've
Second option is a window.
Right. Hopefully, entire screen will work.
No. You don't have to click on your entire screen. You click on window. Yes. Now it is coming.
Right. What can you see now?
Your screen is there. You open your presentation. Yes. Now it is visible.
That's perfect. Okay.
Yes. It is perfect.
Right. And what's this? Oh, that's that. Okay, that's good.
Yeah, it is working.
Whoa, that's a new skill that I've just acquired. Who have we got? Right, thanks for assisting with that. Yeah.
Yes. हाँ जी बताओ. अभी हम सेशन स्टार्ट करके फिर बताते हैं. So, Professor Rees, shall we start?
Yes, yes. Why not? No time like the present.
Okay, thank you. Yes. So, good afternoon and good morning to all of you. So, welcome to second session of first day winter school. We are enough fortunate that we have Professor Rees from University of Bath, UK, and he will be talking about modal selection for inclined Darcy-Benard convection. It is my privilege and honor to introduce Professor Andrew Rees. That Professor Rees is presently working as an associate professor in fluid dynamics, Department of Mechanical Engineering, University of Bath, UK. Before working here, he has worked as a lecturer and postdoctoral research in various institutes like University of Bath, University of Exeter, University of Bristol, and he has completed his graduation from Imperial College of London and his PhD from University of Bristol in 1985. He has a recipient of outstanding contribution to special award for the outstanding contribution to field of fluid mechanics and enhancing the research activity in Bangladesh. He has a recipient of Mary Taker Award of Teaching Excellence. He has given G.I. Taylor Memorial Lecture in Islam. He is recipient of Outstanding Paper of Year 2018 Award in International Journal of Numerical Methods for Heat and Fluid Flow. He has a recipient of Outstanding Reviewer for International Journal of Numerical Methods for Heat and Fluid Flow, recipient of Outstanding Reviewers in 2016 in SME Journal of Heat and Mass Heat Transfer, and he has also Best Reviewer for SME Journal of Thermal Science and Engineering Application. Apart from that, he has published more than 174 international journal paper, 65 conference paper, 7 referred chapter in review book, and 2 books. He has having H index 31 as per Web of Knowledge and 38 ResearchGate, and RG score for ResearchGate is 76.93. His research interests are in instability of unsteady thermal boundary layers, network modeling of porous media, microscopic modeling of local thermal nano-equilibrium, modeling of Bingham fluid in porous medium. He is also the editor of various reputed journal like Associate Editor of Transport in Porous Media, Associate Editor of International Journal of Numerical Methods in Heat and Fluid Flow, Associate Editor of Computational Thermal Science, Editorial Board Member of Journal of Fluid, Editorial Board Member of Journal of Science, and visiting professor of University Paul France, external examiner for MSc and PhD also for various theses. And he has been delivered various invited talk in various international and national conferences. He has published maximum paper in recent years from 2016 to 2020 in the Journal of Transport in Porous Media, International Journal of Numerical Methods in Heat and Fluid Flow, Journal of Engineering for Gas Turbine and Power, International Journal of Heat and Mass Transfer, and many more. So with this short introduction and a brief information about Endurance, I would like to invite Professor Rees to deliver his talk.
Thank you, Professor Tripathi, for that very long introduction. I wish I provided a much shorter CV to you. There's probably only 5 minutes left for my talk now, I think. Okay. Yeah, I almost didn't recognize myself. Sorry, I missed that.
Yes.
Okay. Well, thank you all for being present at this talk. I hope that you'll find it interesting. I hope you'll find it informative. With the various things that have been said about me, then I feel under very great pressure to perform exceptionally well. But you're going to get what you're going to get, I'm afraid. Yeah, modal selection for inclined Darcy-Benard convection. This is joint work with Antonio Barletta at the University of Bologna in Italy. Now, we had a very interesting talk earlier today from Professor Sideshwar, who was discussing Rayleigh-Benard convection, which is characterized by having a layer of fluid which is heated from below. Very, very similar to what you see on the screen right now. There are some differences between what I will discuss and what he was discussing earlier. One similarity is that we have a layer of fluid that's heated from below. I'm hoping that you're seeing what I'm doing on the screen here. It's very strange not to have any feedback, but I guess that's the new modern age. So that's one thing that's similar between the problems. But there are some differences. The main one is that I'm looking at flows through a porous medium. The big change with that is that instead of having the Navier-Stokes equations as the momentum equations, we have Darcy's law, which expresses how easy it is for the fluid to filter through this porous structure. So it's a different momentum equation. The heat transport equation will be the same in effect. So it's a porous medium rather than just a fluid, so that's one difference. Another difference is that we have an inclination from the horizontal, which is measured by the angle alpha. Professor Sideshwar was also talking about having a layer of infinite width. So that's the diagram on the left. I will really be concentrating on the diagram on the right, where we have a cavity. So we have a finite length cavity, so we don't have periodic boundary conditions, but all the action takes place within that cavity. It will be subject to thermoconvective instability. This is what happens when we heat these systems from below. Convection sets in, and that allows for a greater rate of heat transfer across the layer. And that, I presume, is the physical reason why we get the instability. Excuse me. Now, Professor Sideshwar talked about the transition from a zero flow through linear stability and on to chaos in his system. Fortunately, I'm not going to be going quite as far as chaos, although when you see some of the diagrams later, you'll see them as being a little bit chaotic. But I will say that with this particular system, the linear stability theory is well known, especially if it's horizontal, and one can proceed analytically with even with weakly nonlinear theories for that and work out whether convection is supercritical or subcritical. And one can look at 3D instabilities. As long as they're weak, then one can do it all analytically, which is rather good. When the layer is inclined, as we have here, then for the diagram on the left, the layer of infinite length, again, the linear stability theory is well known, and I'll show that now. I'll explain this diagram in a moment. It looks horrible, but that summarizes the stability properties for the sloping infinite layer. Now we've got Rayleigh number as being representative of the buoyancy forces, or the strength of buoyancy. And once the Rayleigh number is large enough, then we will get convection setting in. Horizontal axis is a scaled wave number. And for the horizontal layer, one will have a critical wave number of pi, which corresponds to 1 on the horizontal axis, and a critical Rayleigh number of 4 pi squared. So we can think of that as being 40. What happens next is that if you increase the inclination of the layer, then one follows different curves on this diagram. So this will be mode 1 for the horizontal layer, and this will be mode 2, and this will be mode 3, and subsequent curves increment upwards in angles of or increments of angle of 1 degree, and eventually you get to this red point here, 31.49 degrees, which marks the end of instability. So from the point of view of linear instability, once alpha is greater than that, then the layer is formally linearly stable. So if you give it a small perturbation of any sort, then that perturbation will die as long as alpha is greater than this particular value. And that's of very great interest, because if you have a look at the equivalent fluid problem, then one gets instability at all possible inclinations. So this gives a different qualitative nature to the stability problem. This doesn't tell us anything at all about the nonlinear convection that could take place. And that really is the subject of this particular talk. So here's the question. Is 31.49 degrees the largest angle for which we will see strong convection? We could undertake a weakly nonlinear analysis. I'm afraid I'm still yet to do that. And another question is the onset of convection always supercritical? And although we won't be considering this aspect, this diagram shows the difference between the two. So if the horizontal axis is the deviation of the Rayleigh number from the critical value, so onset happens at 0 on this graph, this will be a supercritical bifurcation. So the amplitude A of convection will increase as the Rayleigh number increases from the critical value. If it were a subcritical instability, then we'd have strongly nonlinear convection at a lower Rayleigh number than the critical value. So these are the things that still need to be found out about this problem, and is on my list of things to do. Okay, well, we've had two very interesting papers appear in the literature in recent years. This particular one is by a pair of Americans. They responded to Antonio Belletta and me. We were guest editing an issue of the journal Fluids, published by MDPI. It was a special issue on convective instability in porous media, and they provided us very kindly with this paper. They presented strongly nonlinear computations. It was an infinite layer, and they presented multiple steady states with this. And for me, the thing that was of interest was that they showed some nonlinear flow patterns for an inclination angle of 35 degrees. So that's greater than the 31.49 that we found, well, 21 years ago for the linear stability problem for the inclined layer. So that was very interesting, and it sort of made me regret that I hadn't studied this problem earlier, because I would rather have liked to have been the first one to have shown that. But oh well, if I'm lazy, this is what happens. Now that was a layer. This is a slightly earlier paper on an inclined cavity. Again, it's a porous medium. And again, these guys looked at strongly nonlinear computations, and they also found multiple steady states. they too found some nonlinear flow patterns for alpha is 35 degrees. I found that actually more interesting than the previous paper, simply because if you have a finite cavity, then that puts extra constraints on the flow. There is less freedom for instability to happen if you confine it in some way. Now, I have to declare a bit more of an interest in this particular paper because the first author, Fernando Guerrero Martinez, was a PhD student at Glasgow University in Scotland with Nader Karimi as the supervisor. And I was asked to be the external examiner for this PhD. So I had the opportunity to read his thesis very, very carefully indeed. And so my initial thought when I saw the claim that alpha is 35 degrees actually gives some nonlinear flow patterns, my first thought was, surely that can't be right. Surely linear theory tells us what's happening. 31.49 is the magic number. But of course, that is the essence of true science. You know, you see a result like this and you think, surely that can't be right. And you go ahead and do something about it, like write a code and find either these people were wrong or they were right. If I'd found that they were actually wrong, well, that would have been pretty bad for the poor student, given that he was actually right. It was something really, really interesting. So obviously he got his PhD and everything. And he's got some publications out of this too. So yeah, I had to check this all myself because I didn't believe the result. Now this is one of the diagrams from his paper. Obviously I saw the early version in the thesis. So this is for a Rayleigh number of 100 and a cavity of aspect ratio 3. So it's 3 in what would be horizontal when the inclination is 0. So length 3 in the x direction, length 1 or height 1 in the z direction. Now, these are his solution curves. So the solutions are against the inclination angle. So horizontal is down here at alpha equals 0. And the vertical axis measures the strength of convection by means of the Nusselt number. This is the integrated rate of heat transfer along this surface in the x direction. Now, I have to tell you what these curves mean. Basically, n equals 1 means that there's just a single cell. So it's a unicellular state that's taking place within the cavity. And this is what happens at high inclinations. And you could almost imagine that if you've got an angle of 45 degrees, you'll have flow going up the hot wall. That's the lower surface. And then we'll come back down the cold surface at the top. So one will have that simple unicellular state. N equals 3 tells us that there are 3 cells in the cavity. I have to inform you I've got the number wrong here. It should be n equals 4. This curve demonstrates that there's 4 cells within the cavity. This is another n equals 3 curve that the authors found. Now the question is, well, we've obviously got some multiple steady states. We've got possibility of 4 cells, 3 cells, or 1 cell here. And if you were to set up an experiment to do this, or a numerical experiment whereby one maybe, I don't know, calculated this solution, the n equals 3 solution with 3 cells at an alpha of 15 degrees, and then decided to use that solution as the initial condition for maybe the next value of alpha on, then you'd trek along this curve gradually. And likewise with an experiment, if you increased alpha very slowly, then you'd move along this curve. Eventually the Nusselt number would start to decrease, and at this point everything would suddenly change to the 1 cell state, catastrophically. And indeed that's what happened with my numerical simulations, my finite difference simulations that I used to check the students' work. And likewise, if you start up here on the n equals 1 curve, one can move down slowly quasi-statically, if you like, and then eventually you'll have a big jump up to the n equals 3 solution. So that's what the dotted lines mean. That's what would happen in practice if you were changing alpha very slowly. So there's a hysteresis here. And likewise, there's n equals 4 solution. That would cease to appear, and you'll jump up to the n equals 3 solution. So I guess this destabilizes, and everything evolves to a 3-cell state. So this is the sort of thing that happens. Now, those folk who know about bifurcation theory and have some experience will also know that curves do not terminate in this fashion. And the question is, what happens after we pass this fold or this turning point or whatever you call it? And what happens down here? Do these curves join up in some way behind the scenes? And what happens to this? So these are also questions that I wish to ask as a result of this. And one cannot answer those using finite difference methods, simply because they, as, say, a time-dependent solver, or they as something you solve iteratively, like Gauss-Seidel or successive over-relaxation, or maybe even multigrid, those will only converge to solutions that tend to be stable in terms of time evolution. So one cannot use those methods to work out what happens beyond the end of these curves. But these curves should be, and indeed must be, continuous in some way. Okay, so that's really the basis of this talk. It's to find out whether, what happens when we vary the inclination angle. We need to find out about the modal selection, how many cells that we've got, will we have, what happens to those curves, and how high can the inclination be for convection to take place. Right, well, we'll answer those in a few moments, but this diagram defines the problem that I'm solving. So again, it's non-dimensional temperature equals 1 on the lower surface, equals 0 on the upper surface, so we're heating from below. It's insulated d theta dx on the side walls. X is in the direction that's parallel to these isotherms that we see, and the stream function is 0 along the boundaries, so that it's all nicely impermeable and all the fluids contained within the cavity. X ranges between 0 and L, so that's x equals L, and this is x equals 0, and its Z goes from 0 to 1 as we go up the layer. I've written the stream function version of Darcy's law together with the buoyancy term on the right-hand side that's appropriate for the Boussinesq approximation and given the direction of the coordinate system relative to horizontal. So this is the buoyancy term. This represents Darcy's law, which in effect is velocity is equal to minus the pressure gradient plus any body forces that happen to be around. And this is the familiar heat transport equation. I've non-dimensionalized these at the outset, so that we've only got, I guess, two main parameters, the inclination alpha and the Rayleigh number, which in this context is the Darcy-Rayleigh number, which contains the porous medium permeability as part of its definition. But other than that, it plays exactly the same role as the normal Rayleigh number does. The larger the Rayleigh number, the higher the buoyancy forces. So I've repeated the governing equations here, and given that I'm intending to apply a spectral method to this, I found it much more convenient to subtract out the basic state. The 1 minus Z, that's the color scheme that you see here. So that's 1 minus Z is the basic temperature profile. So I'm going to subtract that out, so that leaves me with all the boundary conditions being homogeneous, and that will assist in the use of a spectral scheme. So by doing that, I'll get this extra red term on the right-hand side of the momentum equation, and this extra term that comes from the d theta dz term here. So now I've got an inhomogeneous momentum equation, but I've got homogeneous boundary conditions, and that works nicely from the point of view of a spectral scheme. Now this is when it all begins to look nasty. I've reproduced these equations, the governing equations, and the natural thing then is to introduce, I guess, what would be a double Fourier series, or double half-range Fourier series, so as our spectral scheme. The vertical components are sine of j pi z, so that those are both zero at both z equals 0 and z equals 1. And in the horizontal direction, the left-hand edge is x equals 0, so hence the sine is 0. At x equals L, so that's the whole length of the box, this sign needs to be 0 as well. So that constrains us to having k equal to pi over L. The aij's are the unknown coefficients, and that's they will be computed. The corresponding terms for the temperature, basically we need cosines in the x direction or constants in the x direction in order to satisfy the insulating conditions on those side walls. One could stick a half in there, as one often does with some of these things, but given the complexity of what's about to happen, it doesn't make too much difference whether you do or you're not. Don't do or don't do. Right. So the stream function equation now becomes this. So this was our inhomogeneous term, and these three terms, if I go back a slide, they come from d theta dx and d theta dz, where theta takes these forms. So I get this horrible mess. It is actually worse than you might think, because this is the stream function equation, and it rather likes to have signs in both directions in order for things to work really quickly. I've got a cosine there, and I've got two cosines here, and I've got something that's constant here. So but this first right-hand side term and the third and the fourth will need to be expanded further as double half-range Fourier sine series. The second term is perfectly fine, much to my relief. So this is what comes out. So we've got at worst a quadruple summation. It looks nasty, but it's not too tricky to code. You'd be glad to hear. So all one needs to do is to run through these loops, and then one can slot that coefficient into whichever element of the array represents the aij quantities for the stream function. So although that looks a bit messy, that is not too bad. Unfortunately, when it comes to the heat transport equation, that is worse, because we have these products of terms. So it involves the stream function and the temperature, and we've got these products of sinusoids. So the organisation of that within the code is not the nicest. I've got a few terms here that are nice and direct, that can slot in quite easily. But the upshot is that given that we've already found A in terms of B, in all cases, we have now got what will be quite a large number of equations in the same number of unknowns, and they're nonlinear. So the way to go then is to use a Newton-Raphson code, and it is that fact that allows us to be able to compute solutions which are formally unstable in real life. In some cases, the number of variables numbers in the hundreds, so the only way that one can legitimately write a Newton-Raphson code is to use numerical differentiation in order to find the Jacobian matrix, or the Frechet derivative, in order to implement the method. So as you can imagine, this this sort of coding has to be done very, very carefully. The summations themselves have to be analysed very carefully, many sheets of paper, and a lot of headache with the coding and a lot of checking along the way in order to make sure that one has a code that is as error-free as quickly as possible, as is able. So the other thing is that because I wanted to go around the corners of some of these curves, we need to have a curve tracking facility. So added to all of those, I've got one extra equation which basically stops me going too far along the curve. So one's looking at a distance along the curve, or a scaled distance along the curve, and making sure that your code converges to something that is a non-zero distance away from where you started. So you have to compute all the variables, the Rayleigh number and the wave number. Sorry, the Rayleigh number and the inclination angle in order to go around some of these corners. And of course, after all of that, you really, really do need to check that the computations are correct against a very substantially different method, which I'll do in a second. Then, assuming that everything compares well, you're in a position to find out if everybody else has done things correctly afterwards. So I'll show you a little bit of that. Also, for the summations themselves, how many terms should one use? So accuracy is also important. But given the quadruple summations, you really need to be able to get these computations done before it's time to retire. Okay, here's my main validation. If we look at the right-hand table first, this shows the results of one computation. So it's for Rayleigh number of 100. So it's moderately strong convection, inclination angle of 20 degrees. That's a good one to use because, again, it's not too large, but it's not too small. It also involves every single term that you saw a few slides ago. It's a unit aspect ratio box. That number doesn't really matter too much, but given that it's a square box, computations will be relatively quick, unlike, say, a 5x1 box. So these are the number of modes in the two directions. The first one is sort of one mode in the horizontal direction and two vertically. Now, if you listen to Professor Sidishwar's talk earlier today on the Lorentz system for modelling Rayleigh-Benard convection, this 1x2 spectral method is basically the same as that. It'll reproduce precisely the results of the Lorentz system. And I'm going to monitor the accuracy of the solutions by the 1-1 temperature mode. So that is basically the onset mode. And the B02, so it's 0 in the x direction, 2 in the z direction. So that's the first nonlinear interaction of the primary mode with itself. So I'm using those to check my accuracy. It actually turns out that it's better to look at even numbers for nz, and then x being one less than that. So as you can see, I take more and more modes in the spectral scheme, and the values for B11 suddenly you find after about 9x10 set of modes converges very, very rapidly to these that I've coloured in red. So these are in fact correct to 6 decimal places, or at least you won't get any change after the 17x18 case. On the other hand, I've got over here on the left-hand side results of second-order finite difference computations. This means that I've used a 16x16 grid, 32x32, 64x64, and so on. And the iterations for that went down to machine accuracy just to make sure that I got as much precision in solving the difference equations as possible. Now, I have to explain, I have got spectral mode amplitudes here. Those don't come out directly from a finite difference calculation, but if you were to multiply by the appropriate signs and integrate, you can obtain those Fourier coefficients from the finite difference solution. So that's what I did. I used the trapezium rule in both directions to find these data. And so they compare very well, as you can see. But they're second order accurate. This isn't good enough yet, even at 128 by 128. So I used Richardson extrapolation to remove the second order errors. So this one that I've called 32, n equals 32, that involves 4 times the raw data for n equals 32 minus once times the n equals 16 and divide by 3. So that's the standard Richardson's extrapolation for a second order accurate method. And that yields this value, and likewise for the others. And then I can do the same again with the fourth order Richardson extrapolation formula, and I get these out. And as you can see, the red font is identical on the left to what it is on the right. So that was indeed a celebratory day when that happened, as you can imagine. So that tells me that the code that I wrote is correct, given how general the case was that I've studied. And so, of course, we can now check other people's results against that. I did decide to go for the this resolution, 9 by 10. So I had maybe errors in the 4th decimal place, just about, which I thought was good enough for this. So for an L equals 1 cavity, 9 by 10 is chosen, and so therefore if I've got any cavities that are larger than L equals 1, I'll take 9 times L in order to get the same resolution spatially. And that's why long cavities are quite tricky to solve, because the number of modes goes up quite rapidly, and when you multiply by the fact there are 4 summations and you've got to iterate, it's quite time-consuming. Okay, let's compare against Guerrero-Martinez's results. So this was their original diagram, excuse me, which I then, because I scanned that in with the JPEG, I managed to clean it up by getting rid of the dots, and I've also rescaled the Nusselt number so that it's the Nusselt number per unit length. And this is what I got with my code. So we can see all the dots have been joined up. So the n equals 1 solution here turns a very, very sharp corner. And it is a curve if you're looking closely. And if I do very, very small steps along the curve, then this is a proper curve. It isn't just a corner. It does turn an actual corner. And it moves up and round. The n equals 4 solution is also mimicked here quite well. I've also got other solutions here. This is an n equals 2 solution, this rather faint dotted line here, and we've got more structure happening here. So all the things that you see here that are not present on the left-hand side are solutions which were either not looked for by Guerrero-Martinez et al., or else are formally unstable, in that if I were to supply, say, that solution there, where the arrow is pointing, as an initial condition to a finite difference solver, then it would diverge away to some other solution. Now, if I look, this is the same computation. I'll go back a page. The right-hand diagram is the right-hand half of this. So this looks even more impressive, I suppose. I've even got an n equals 5 solution that I managed to find with this particular case. Now, the question is, I've labelled all of these n equals 1, 3, 4, 5, 2, whatever. What do they represent in real life? I've got a few pictures coming up next to illustrate those. I think the first one's for alpha is 30 and n equals 1, so it's a relatively weak solution. Yes, that's the one. Alpha is 30 and n equals 1. We have a circulation where the flow goes up the hot surface, around, and then down the cold. we've got a couple of weak co-rotating cells here, but in essence, it's an n=1 solution. And you might be able to detect just in the background the isotherms. I've drawn those in as dotted lines. They don't deviate very much from straight lines, so that demonstrates to me that this is a relatively weak flow. Unlike this one, where the isotherms go around through S shapes. So this is actually a really strong flow. Where is that? Alpha is 25, n=3. So there's 25 and there's n=3. Yeah. So that's a much stronger flow. The Nusselt number is much larger. If I go to 3 other cases, which will also illustrate what happens with many of the other figures. This is an α=5 degrees case, n=3. This is another α=5. In fact, all 3 are α=5 degrees. n=3, n=3, and an n=4. Let's go back and find where those are. So there's 5 degrees. So that was the upper solution. This point on the blue line was the middle solution, and this point on the purple dashed line was the lower solution. So 3 cells, 3 cells, 4 cells, but the second 3-cell solution is weaker. Can we explain it? Well, yes. If we look at the isotherms, they are bent downwards here, so the circulation of this cell is anti-clockwise. And more to the point, this flow is going up the hot surface, so it is being aided by the natural buoyancy force along that surface. Same happens for this cell. You can see the isotherms behind, they're being pushed upwards, so this is also anti-clockwise. So it's the natural direction for the cells to take in an inclined layer. This one goes in the wrong direction, so to speak, so it's anti-natural, if you like. And the upshot is that the natural cells are longer than the anti-natural ones. The second solution is one that I've called anomalous, and that's because everything's going the opposite direction. So the 2 outer cells are anti-natural, whereas this is the natural direction. So again, this one's wider than these 2. And then with the 4-cell solution, this is going in the natural direction. Again, you can see the isotherms behind. This cell is shorter, but it's going the wrong way. This one's long again. It's the natural circulation, and this one's short. So, so for the odd-numbered modes, we can have 2 different types of solution, the anomalous solution and the natural solution. For the even-numbered modes, well, it wouldn't make any difference if the overall circulation were the opposite. You'd have the same picture, but just flipped about the vertical axis. So there are no anomalous solutions because one of the end cells will always be, I suppose, anomalous or anti-natural in its own right. If I go back to this diagram, you'll see that I've coloured the curves according to the mode number or the number of rolls. As part of the computation, one of the bells and whistles I put in at the end was an estimation of the number of cells there were. And to do that, I computed the stream function. So in this case, with a stream function equals 0 here, it'll go up to, let's say it's a maximum, down to 0, negative, back up to 0, and then positive again, and then back down to 0. So I was able to compute how often one passes a 0 streamline, and then of course one adds 1 to that, and that's the number of modes or number of rolls that one has. One can play the same game with the isotherms. One could subtract out the basic state and play the same game with the isotherms, and one will always get a slightly different number of modes from that, but they're always roughly the same. And so every case I did for every inclination angle or every Rayleigh number or every whatever, I also outputted the value of n, and so my plotter will actually change the colour depending on how many modes there are. So that gives us a nice visual impression of what's happening. So yeah, tricky code to write, but then quite a few sort of post-processing things were required as well. Okay, on to the results. This is a boring one first, but I guess it's illustrative. So this is, again, Nusselt number. It's for a unit cavity. I've got the inclination varying from minus 180 up to plus 180. When it's 0, I've got heating from below. When it's 90, the heated surface is now vertical, and 180 represents heating from above, and of course one won't get instability with that. But one can see that for Rayleigh's 10, 20, 13, 40, as soon as the inclination increases, then one gets a circulation, and therefore the rate of heat transfer increases and eventually decreases again. So that's standard. There's no instability where at Rayleigh number of 40 at the most. The critical Rayleigh number for a unit cell when it's horizontal is 4 pi squared. So really this is just the effect of conduction, even if it is nonlinear. Now when we increase the Rayleigh number to 50 and then on up to 100, we get this rather strange thing happening. So if I start maybe at 60 degrees, we've got quite a strong convection cell here. Obviously these are all unicellular motions, and as we decrease the angular inclination, then the direct action of the temperature of the heating on the lower surface, that will decrease, but that also allows the buoyancy effect to increase, but the overall effect is the Nusselt number decreases. So down to here at the Rayleigh at alpha equals 0, this is the nonlinear standard porous Benard Nusselt number, and so inclination will increase that. Inclination also causes the cellular motion to get stronger, but when it's in the natural direction. If I now go backwards, say again, that thought experiment or perhaps the numerical simulations, if I go backwards to a slightly negative inclination, the cellular motion will still carry on in the right direction, or carry on in the same direction, but it's now anti-natural, and hence the amplitude is smaller. And eventually that goes back down to Nusselt number equals 1 at inclination equals 0. In practice, if you were to use a finite difference scheme, you'd be able to compute all of these solutions down to just about where we get a vertical tangent on these curves. So we get both the natural and the anti-natural solutions automatically using this spectral scheme. Now, I've gone up to Rayleigh number of 100. The two-cell mode has a linear onset at 6.25 pi squared, or 62.5, probably closer to 60. So let's take a, and I haven't shown these on this particular picture, but this is what happens. So Rayleigh number is 70. Remember, 62.5 is the onset for mode 2 at this critical at 0 inclination. So we do indeed have a nonlinear solution, and it bifurcates away from the n equals 1 solution. You might just be able to see that there's some black dots there, so the code has identified that as being essentially one cell. So really what happens as one moves sideways here, as the inclination increases, is that one of the two cells in the box gets stronger and the other one gets weaker, and eventually disappears, and then we have the bifurcation away from the pure n equals 1 solution. The higher Rayleigh number, same thing, it's just stronger. To Rayleigh number of 90, things are now beginning to look a little bit more interesting. This n equals 2, the two-roll solution, develops a loop, and we have a small section down at the bottom of this particular n equals 1 loop, which the code identifies as being 3 rolls. As we can see, when the Rayleigh number increases a bit more, we've got an even longer section of curve for which we have n equals 3 This loop has now got bigger, 2 different solutions. For Rayleigh number 120, we're now actually above the critical Rayleigh number for 3 roles in the unit cavity. So that's now the green solution. That manifests itself as a loop. So this is the nonlinear solution, and that wouldn't be found using the finite difference method. It may well be, I haven't checked it, but it may well be that one could find the n equals 2 solution now, because it's quite strong compared with the n equals 1 solution. So we'd see the n equals 1 solution, single row solution in practice. I would probably see the n equals 2 two-row solution in practice as well, but I'm pretty sure one wouldn't be able to compute this one with a finite difference scheme. At 150, things get more complicated, as you can see. And I've not shown the n equals 4 solution, and I think n equals 5 is a possibility here too. Right, well, that was beginning to get a little bit complicated. Let's see what happens when we've got a cavity of aspect ratio 2. So if we have a horizontal cavity of aspect ratio 2, then the 2-row solution has critical Rayleigh number 4 pi squared. N equals 3 follows soon afterwards, and n equals 1 and n equals 4 are at 62.5 roughly. But you can see they're beginning to crowd in. There's quite a few here at or under 100. So we've seen something like this before. So these are the low Rayleigh numbers. So these are really just the standard direct effect of buoyancy, but not instability. On the other hand, when we look at the Rayleigh number equals 40 solution, so we're up to 20 degrees, both sides, relatively weak Nusselt number, so it's 1.4 at most. But we have this small range over which the n equals 2 two-row solution does appear. But as I say, it's quite weak. So I guess if you manage to set that up and then were to gradually increase the inclination, one would move to the right and drop down to an overall unicellular motion. Okay, RA equals 40 goes up to 45, and this loop for the 2-row solution gets larger and gets larger again. At this point, we've got a nonlinear solution for 3 rows. So that has appeared. That was about 46 was the critical Rayleigh number for that. And then it begins to get incredibly complicated. We've got a very strange structure happening here, and we've got a loop happening just here as well. In fact, that curve moves downwards from the unicellular high inclination state. It loops, turns into a 3-cell mode, and then goes all the way, passes all the way through here. On the other hand, the n equals 2 solution, it basically moves around and then comes back as and becomes a bifurcation off the green n equals 3 mode. In fact, that can be seen more clearly over here. And we've also got the n equals 4 solution making an appearance at this point. So as you can see, it's becoming quite complex. They're quite pretty diagrams. They certainly show that for a Rayleigh number equals 70, we've got a large range of inclinations over which we'll see the natural 2-cell solution. But that quickly gives way, maybe about alpha equals 12 to the unicellular state. 80, 100, we've even now got an n equals 5 solution, and things are becoming virtually unmanageable in the middle there. In fact, it becomes quite difficult to be assured that you've got every single solution. So if you think back to the Guerrero-Martinez curves, and what we've got here now, there's quite a substantial difference between the possibilities of the 2 different numerical methods. This is an intermediate case with L equals 1.5. So we have a range over which 2 rows has the largest Nusselt number, and although it doesn't bifurcate off the n equals 1 solution, nevertheless, if you were tracking sideways from zero inclination, one would presume that instead of dropping off the curve, one would drop up to the n equals 1 solution there. Rayleigh number equals 70 and an aspect ratio 3 curve. I'm going to go through these quickly because one begins to lose the vocabulary to be able to deal with some of this. You can even see that I've not completed these diagrams. One gets to a point where you think, well, is it worth the effort? That's a Rayleigh number of 100. That's one we saw before, in fact. That's the Guerrero-Martinez one that I've now put into the colour scheme that I've used for most of this talk. So that's n equals 1, n equals 3, the orange is 5, the blue is 4, and the red is 2. And we've got the extension back down to zero inclination with a Nusselt number of 1, so the zero state, basically. With 5, L equals 5, well, the only thing I want to say about that is that when we've got large aspect ratios, we begin to get multiple loops like this happening. Don't ask. I haven't a clue. We've got a lot of action happening here as well, but there's clearly something else happening in there that I really haven't got the energy or desire to compute. But one of the things that's really interesting here is that here we've got an n equals 6 solution, which appears to have the largest Nusselt number. Then as the inclination increases, n equals 5 forms the largest Nusselt number, so that presumably is the preferred mode. And as you increase the inclination angle, this could be done in practice, I suppose, that solution will disappear and we'll get an n equals 3 solution, and then you drop down to n equals 1. So there's a cascade, I suppose, of switching of modes from 6 to 5 to 3 to 1 as the inclination angle increases. So that is, I think, of particular interest as far as modal selection is concerned. Here's L equals 6. So now we've got an n equals 7 solution forming the most unstable mode, or at least the one with the highest Nusselt number. That will turn into a 5, which will turn into a 3, which will turn into a 1 as alpha increases. Clearly there's a lot missing out of here. I haven't finished these curves. This looks like somebody cheering, which is probably quite appropriate given I'm only a few slides away from the end. But that is a legitimate computation, honestly. Everything I've shown you has actually been from the point of view of alpha changing. That seemed like the appropriate thing to do, given the central role that alpha played in that original stability analysis, with the 31.49 degrees being the largest inclination for linear instability. But with these sorts of problems, it's usually the case that people increase the Rayleigh number and see how properties change with that. So I have just recently started doing that, and here's just one example of that. So it's modest inclination, 10 degrees, aspect ratio 2 box. The Rayleigh number just goes from 0 up to 150. Again, this is the Nusselt number there. So we have the unicellular pattern, which when the Rayleigh number is below 4 pi squared is the only thing you'll get. There's no instability. And in fact, that curve keeps going upwards as a potential solution to the equations. At relatively high Rayleigh numbers, the largest Nusselt number is given by an n equals 3 solution. But we do have this patch with n equals 2, the red curve, forming the most highly convecting case, at least in terms of the Nusselt number. But this curve is weird because it goes along here and then almost doubles back. It's not quite the same curve. There's a very distinctive loop, and then it comes back this way. So again, n equals 1 presumably loses stability to the n equals 2 and then to n equals 3. So again, we've got a cascade of modes modal interactions or modal changes happening as the Rayleigh number changes on this occasion. So, as you can see, final comments. This task is far from complete. It's actually turned out to be a lot more intricate than I first thought. I still think the work is very, very much of great interest. There's a lot of insight that one can get from looking at these things. Of most interest are the cases when L takes large values, so large aspect ratio. But of course, as I say here, the arithmetic is huge. 540 modes to solve when L equals 6. Quadruple loop means that you've got an absolutely massive number of computations to undergo for every point within that quadruple loop, and then you've got to iterate. And the iteration takes place via numerical integrations, so you've got to have at least the equivalent of a fifth loop in order to be able to do that. So it is not at all pleasant, and it becomes very, very slow once we're beyond L equals 3, L equals 4. I cannot be assured of getting every solution branch. With L equals 1, maybe, a unit aspect ratio box, yes. Possibly 2, maybe even 3, but after that, it becomes incredibly tricky, especially given how long the code takes to run. That last figure shows that variation with RA is also important. So I guess some of those will need to be done. And then the question is, what can one do to write a full paper on this? I guess the principle is to get over some sort of idea of a global behavior of the system, but one doesn't want to overload the reader or indeed the journal with massive numbers of figures. But we found a rich bifurcation structure. It's very complicated, and strong convection does arise even in the cavities. We found these things as well. So that's about it. I've got a list of references here. The ones in red are the primary sources, the two nonlinear papers that I quoted at length, and the one of mine from 21 years ago. So that's about it, I think. I'm sorry it's not the full 90 minutes. Tried my best to stretch it out. I hope that's okay.
Okay, sir. Thank you. Thank you very much for giving very interesting and informative information about the Benard convection, especially for the inclined porous layer and the inclined porous cavity. And you have discussed various, stream function equation and solution procedure, how to solve that equation, and also many results, especially the variation of Nusselt number with inclination and other parameters like Rayleigh numbers. So is any query or doubts from the audience? Then Professor Rees will be happy to discuss. Any query from the audience? From the
I hope people didn't fall asleep. Ah, okay.
I think there is no query from the audience and participant side. So thank you, sir. Thanks again.
If people wish to have access to the slides, then I'm very happy to provide that.
Yes, sir. Yes, you please provide your PPT, so I will share to all the participants. That will be great.
Okay, my pleasure. I mean, it's been an overload of color, I think.
So thank you. Let us have a big hand for Professor Rees. Please unmute your mic and let us big hand for Professor Rees.
Oh, thank you. Thank you.
So thank you, sir. And
Okay. Thank you.
and participants are requested to attend inter school. So next session will start on tomorrow from 10 a.m. as per the Indian time slot. So all are requested be there at 10 a.m. Professor Rama Govind Rajan from TIFR Bangalore. She will be talking about some aspect of particulate flow. So you all are requested to be there and attend that session. So thank you very much for listening, Professor Rees, and thank you for your active participation. Thank you, Professor Rees, for giving your
My
valuable
pleasure.
time.
My pleasure. I've put the web link to my slides on the chat if anybody's interested.
Yes, yes. Yeah, your link is there.
Yeah.
Yes. Thank you. Thank you for sharing your details
Okay.
with us.
My very great pleasure. Thank you.
Thank you, sir. So we will looking you in future at NIT Uttarakhand. It is very beautiful place.
Yeah.
So we'll invite in future. Yes.
In the first instance, I'm looking forward just to the possibility of being able to travel somewhere.
Yes, 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 sir. We are looking.
Yeah. Okay.
Thank
Okay. Right. Time for coffee. Right. I'll see you again.
Okay, sir. Thank you. Thank you very much, sir.
Okay, thank you. Goodbye.
Bye, bye, sir. Thank you, everyone, for joining.